My name is Leonid. I'm an SRE at Dropbox, so I work here in Dublin. So I work in Dropbox for about a year, work in infrastructure team. So basically what I'm working on is AWS infrastructure, supporting it for Dropbox. So in this talk, I'm gonna speak about how we build Python packages, how we make sure the Python package is hermetic, what it means, and how Bazel helps us to achieve that. So can anyone raise hands if they know what is a Bazel build system, or anyone play with it? Okay, a few people. Cool, yeah, so I'm just gonna first of all cover our Dropbox environment in terms of how we push code, how we deliver it, and how the environment looks like. Then I will give a quick Bazel overview. Then I will describe basically how we use Bazel and what are the key takeaways, what were the steps we've taken to adopt it at Dropbox, and at the end there will be some time for questions. So let's start with Dropbox environment. So it's a bit of a challenging environment. So we have a code base that is mostly Python, and it evolved organically over the years. So there's a lot of tricky corners and not obvious things. So specifically, in this picture, I want to explain how it basically the workflow looks like for the developer. So everything starts there on the left with your VM, where you have your code repository. So you write your code, it's stored. So we have one big Git repository, so it's kind of monolithic. Then we have a system called Fabricator. We use that for code reviews. So once your code passed code review, it goes up to a system called Changes. It's actually a continuous integration system written by Dropbox. It's open source. It's on the GitHub. So basically, it runs a set of tests. And if that's okay, it then conducts other system called YAPS, which stands for Yet Another Package System. This is actually our deployment system that deploys code onto a production fleet. So what it does, it basically issues a RPC request to a set of machines called package builders, and they take Git repositories and input and your commit and produce something we call package. So package is really a squashfs image. So squashfs is a file system image. You can find it on there is a Linux live CD. It often uses squashfs. So basically it's a file system in the file, and you can mount it in Linux. So it's supported by Linux kernel, this squashfs file system. So let's now zoom in a little bit into how this package looks like inside. It's another picture here. So on the left here we have squashfs image. So basically it gets mounted onto /mnt service, and that's where the code will reside on that particular service. So inside the package we have binary, so that will be your binary, your daemon that you will run. There might be some libraries, some data in that package, like a static web file, static like images, CSS, something like that, or some bits of configuration. Another thing here that is not marked as dashed lines is a implicit dependencies on things like Debian package. So for example, if you're running and you use a Redis database, you would install Redis via Puppet, not via your package system. So it's independent system. So install Debian via Puppet system. Then every machine in our production has a copy of the whole repo. So your Python code might import something that will reside in that /repo global repository on the machine. And another thing we use, it's a package system called Encap. So it's a package system from the 90s. It's like ad hoc. Basically, your compiled binaries delivered to your production fleet via rsync. Also, a repo is delivered via rsync. So why I'm saying this is bad is because these systems, they're global. So once there is a new version of some deb, it usually gets deployed globally onto the whole fleet. And this deb might be used by different services, and some services might be not compatible with the newer version. So there's a danger of breaking something that you are not aware of when you're updating either some Debian packages or Encap packages, or just updating something inside the repository, because every machine will get a copy of it eventually. So, and yeah, so we use Ubuntu in production, so that's kind of our standard environment. So just to reiterate, like what issues we had with this environment where one service can have this implicit dependency is that when you look at the Python code, you see from X import Y, and so I often get this question like, where is X coming from? Like, is it something inside the repository? Is it come from Encap? Is it installed by Debian? So it's not obvious how to update it or where the dependencies actually is. So this can lead to issues like cyclic imports, for example, where one part of repository depends on another, and so you have to resolve that into runtime and all sorts of bad things like there is code that actually does a dynamic imports inside a function, and this is used to resolve conflicts. So this kind of summarizes the non-hermetic packages. I was looking for like how to explain what is non-hermetic or hermetic means. So this is not hermetic. So these piles of cardboard is your package, your code, and as you can see, it's leaking bits and pieces around. And yeah, so what the requirements for the new system? Basically, what we want is a produce hermetic package. So we don't want that these implicit imports, so everything should be contained inside a service package, and the builds should be reproducible. So you build that in your laptop, in your VM, in the testing changes builder, and then you build that in production via YAPS. It should be the same package. Another thing we wanted is that explicit dependency tree. So there's a picture there. So the circles is your Python packages, and you can see like which library, you can trace which library your service uses, and is it part of repo, is it Pypi dependency, is it a Debian package? So being explicit about what your dependencies is. And yeah, so just to reiterate, we use a monolithic repository, so we have one big Git repository where every server code lives in. So now we're gonna switch to Bazel. So Bazel is basically, it's an open source build system. It was open sourced by Google I think in March 2015. So it's as Google says, it's a core of their internal build systems called Blaze, and that they're using it for multiple ages. So it's stable and rock solid. It's designed to build a monolithic repo from source. So everything's designed to build from source. It's also language agnostic, and it can build anything, any language, or any artifacts. This is useful for Dropbox because we have not only Python code, we also have Go code and a Rust. So using this single system to build everything will be really helpful. And another thing about Bazel, it has a DSL for writing your build targets. It's a subset of Python 2.6 called Skylark, and it's not actually, so Bazel is written in Java, so this subset of Python is implemented in Java, so it's not called into CPython via a subprocess, something like this. It's a completely re-implemented subset of Java. So, and now, this is a pretty complicated picture, but I try to explain the core concepts of Bazel here. So, workspace represents your whole repository, whole Git repository. So it's a file that's located in the root of your repository. And basically, inside the repository, you also have, so in the middle there are folders with build files. That's your code, that's called Bazel packages. So these are where you put your libraries, services, binaries, what have you. There is another thing here called custom rules and macro. These are called BZL files. This is actually Skylark code that declares some custom logic, some macro that is used by these build files in the middle. So on the left here, starting with double slashes, is something that's called labels. And labels are used pretty much like in Python in import statement, is to identify certain package. So for example, /foobar would identify certain package within your workspace. On the right here, on the right bottom in the circles, there's basically, so Bazel CLI, that's the command line tool you need to run inside your workspace to be able to build artifacts, build your packages. And there's another optional component there, it's called Bazel Server. It's used for caching your build files, your local results to increase the speed of builds. And in dotted lines, that's what Bazel generates inside your workspace. These are actually symlinks to artifacts that were produced as a result of build. So yeah, that's pretty much all the core concept here is a workspace. There's labels, there are build files, and there's a macros and a custom rules. So I was just going to give you 4 examples from, all these examples are from open source project called TensorFlow. It actually uses Bazel as their build system. So I just pull these 4 examples here. So the workspace file is basically this really small file. It's written in Skylarks, which is a subset of Python. So it's just a declaration of workspace name. And it loads some of the custom rules to install the external dependencies. And so below there is a custom rule example of the Bazel rule. This is basically a subset of Python, and that implements building something. So it looks like it's basically a function. And on the right top here is a actual build file. It declares targets, so it's quite similar, quite understandable to have a target name, you have sources and your dependencies, and dependency is specified via labels. And at the bottom right there's a macro, so macro is basically a shortcut for calling, it's like a template function basically. So just want to mention a few concepts that I found in Bazel, kind of interesting, not something that I've seen in other build systems. So the first one is these build rules, they can't do arbitrary I/O. So in Skylake, there's no way to write to random files. So you have to declare all your inputs and outputs. So you can only produce outputs. So I found this really interesting. It's an interesting constraint. Yeah. So another interesting point is that Bazel can build inside a container, so it's something called sandboxes. It's basically, they support it on Linux as like a container environment. So this environment has only dependencies that you've declared. So it's useful to make sure that the build is hermetic in terms of it's not uses some other service that is not declared anywhere. And another one interesting concept is that as part of your input, you also take a compiler. So to build something, you need a compiler, and that goes as an input as well. So that's also a pretty powerful concept. And the last one is the Bazel query. So it's a ad hoc query language that you can use to traverse your dependencies to study like which library depends on what library. It's useful when you do, for example, large-scale refactorings, something like that. So it's basically the second part of the talk. So how we started using Bazel, what is the status of migration and how it went. So migration started around July 2015, so it's pretty early after it was open sourced. And currently we have around 3,000 Bazel packages that totals to over 100,000 lines of Skylark code. So that's a lot. And then we have around 3,000 lines of the custom Bazel rules. This is actually surprisingly small, so we didn't really have to write that much of a custom logic to build our services inside our repository. And we have custom rules for Python, Golang, Rust, Node.js. Yeah, maybe something else. Yeah, that's kind of the main. And yeah, it's still work in progress, so we're still porting our services to Bazel, extracting, specifying dependencies. It's a not quick process. So I just want to say, like, if you want to do something like this, how we started, like where to start. So first thing is to specify external dependencies for your workspace. This means for your repository. So that might be something like, in this example, we have Redis. So we have services that depends on Redis. That means when you build a package, you also need to build Redis. And the way it's done here is actually some engineer internally re-implemented the Redis make files in Bazel. So it's actually this build.redis file. It's around 300 lines of code in Skylark. That's a rewrite of makefile. This basically builds a Redis binary. And another example at the bottom there is when it's too hard to actually build something from source, you can just take a Debian package, like a binary, pull in a binary dependency and put it inside your package. So basically, the Bazel package will contain the unpacked Debian package with a Postgres database that can be used to when you start in your database. So yeah, so we have to, for our repository Dropbox, we have to declare a lot of these external dependencies that it took a while to figure out those, but yeah, it's around maybe a few dozens of dependencies that we have currently. So I want to talk about what is Hermetic packages means and how it's actually structured. So the Python executable that the Bazel is produced, we have a custom rules for that, so we don't use what's currently open source by Bazel. So we had to, I think when we started, it was not really open. The Python rules were not open source, so we had to implement our own. So the format is quite similar to what is called packs, that is used by another build system that's similar to Bazel called pans. So there are a few main things there is that we use a custom Python interpreter, and when the binary launches, it basically has a shell wrapper that sets custom Python path to Python libraries inside that package. And it also sets custom library path to shared objects, so files inside that package as well. So for example, if you use this custom version of a libSSL, so OpenSSL library, it will force the Python package to use custom OpenSSL library. And so how to validate this package is actually hermetic. So one thing that's useful is Bazel supports something called, I already mentioned, called sandbox builds. And Bazel also can run tests. So what you can do, you can run tests inside a sandbox. And if during the test you're using something that is not declared as your input or as your dependency, you'll basically get an error. For example, if you don't have dependency on Redis and you want to use some of the Redis CLI, for example, it will be not there. So this is what can be used to check the hermeticity of the package. So let's talk about the package size. So since every package contains all the transitive dependencies, the packages might be really big. So currently you have a Flake 8, so it's a popular Python library sorry, to link the code, and it takes about 3 megabytes in size. It contains every dependency, it's not that many, but except the runtime environment. So we had to extract this runtime environment, which basically runtime environment is a Debian package that deployed in every production machine. It has inside the Python interpreter itself and a few core libraries. So that totals to 400 megabytes. It also contains Go runtime and a few shared libraries as well, like OpenSSL, something like that. And that's deployed everywhere, and that's not part of any Bazel package. So we use that to save space, basically. And additional tricks we have is that when you build a Bazel package, there is a logic to deduplicate files. So for example, if you have two packages uses the same library, but different versions, and some of the files they're exactly the same, one file is replaced with a hard link. So that's also can be used to save space. So what are the key takeaways? So what I observed during that migration process went well and not that well. So the first one is the Bazel is really, it's a complex framework. It's not like a similar system. It's not as easy as makefiles that everyone used to. It takes a while to learn, so it's a pretty steep learning curve. And if you're working as an infrastructure team where you're actually migrating your repository, expect a lot of questions from application developers that will actually write the Bazel rules, so prepare tutorials and examples specific for your environment. And Bazel is also only one piece of puzzle, because we had to roll out our runtime environment, change the way how unit tests run, change the way how integration tests run. So it's really a lot of dependencies outside of the build platform. And another thing that we found out is like sometimes you have to write too many build files. So one example is Pypi dependencies. So we didn't want to write it manually. For example, a build rule for requests library or something like Flake8. So someone wrote a script to actually generate these build files. So I think we have a few hundreds of those actually generated build files for the Pypi packages. So it's a Python script that basically constructs a list of dependencies and then just generates a build file. So that was pretty useful and it saved a lot of time. So yeah, I think that's pretty much it. So yeah, if you have any questions, feel free to ask or email me.